Welcome to Math 31. This is a lesson on implicit differentiation. Important topic. You'll end up using this an awful lot in one form or the other throughout the rest of the course. It takes a little while to get it down, but once you have it, it's pretty much there for good. Some of the questions can get a little messy, so you have to be advised of that. Definitely on your exam you will get at least one, maybe two of these type of problems. Now where it all starts is, first off, with this basic quadratic function, y is equal to 2x squared minus 3. You would say that y is defined explicitly in terms of x, and really it just means that the y is isolated. This is good. If you have the y isolated, you're able to differentiate it very easily, find dy dx. You can graph it on your calculator well. In fact, you can do anything even by hand. Hand sketching is easier this way. You can recognize transformations. So this is really ideal. What's going to happen, though, is that you frequently encounter expressions where that is not the case. Now this one first, x squared plus 4 plus y squared equal 4. X squared over 4 plus y squared is equal to 4. This is an ellipse, if you think back to your Pure Math 30. And the y is not isolated. So we would say that y is defined implicitly in terms of x. So y is not isolated. This presents all sorts of problems. You can't use your graphing calculator, for one. And you also can't make the same observations that you could otherwise if y was isolated in terms of like transformations. It can be done, but it's a little more difficult. And it also is harder to differentiate. So if possible, you want to isolate y, and then you can differentiate it or do whatever. So if you can, you want to isolate the y. Now there's been lots of questions where you won't be able to do it. This one you kept the y squared on the left, bring the x squared over 4 to the right, and then take the square root, and you'll get plus or minus 4 minus x squared over 4. Now with the chain rule, you could very easily differentiate that. So it's not a big problem. This is a simple one, though. They're not always going to be that easy. And in many cases, it's just easier to do implicit differentiation anyways. So let's launch into a few, and I'll go through a few of these, and I'll show you how it all works. Here's a circle. X squared plus y squared is equal to 4. Now, I know you could isolate y pretty easily in this case, but I'm not going to bother. To differentiate, we use, whether you think about it or not, you use the chain rule. And the chain rule is for composite functions, and it really is for when there's more than one function going on with the expression. And it does apply for questions like this, because we want to find, I just said differentiate, but we're going to find dy dx, the derivative of y with respect to x. And we differentiate each of the terms with respect to x. So I'll make a little note. Differentiate each term with respect to x. So 2x squared is not a big deal. We can differentiate that one. And let me write this one out first, just to make it very formal. So differentiate that with respect to x, then we differentiate y squared with respect to x, and then we differentiate 4 with respect to x. So the first term is no problem. The derivative of x squared with respect to x is 2x. The second term is a problem, because we're differentiating it with respect to x even though it's a y variable. So the chain rule comes in is because this y represents an unknown function, basically. So to differentiate it, we do the chain rule, meaning that we go 2 and then y 1. But then we have to, as always with the chain rule, you differentiate the inner. So to differentiate the inner, we simply write that as dy dx. We can go no further because we don't know what y is. And then, of course, the right side is equal to 0. So 2x plus 2y dy dt is equal to 0. So this is the key step. Anytime you try to differentiate y with respect to x, you don't actually differentiate it. You just write it as dy dx. And then you isolate that variable. So 2y dy dx is equal to negative 2x. And then when you divide out by 2y, you'll get dy dx is equal to negative 2x over 2y. So dy dx is equal to negative x over y. So very often, when you differentiate implicitly, you end up with y back in the variable. Now, once in a while, people will go further by replacing y with whatever it represents in the equation, but typically not, because you can do most everything you need with it in this form. Now, the method that I tend to use for these is I use the y prime notation. So I'll show you what I mean. What I would do with this, just for my own work, and remember, using y prime instead of dy dx is for that reason. When you're doing your own thing, you'd use y prime to keep it tidy, and then when you're done, you put it in more formal, a better language, such as Leibniz notation. So what I would do with this is I would go 2x when I differentiate it, and then I would go plus 2y, and then I just go y prime, just to keep it tidy. And the reason for that being that I'm clear that I'm differentiating it with respect to x. So y prime doesn't show that. It says y prime. It doesn't tell you what variable you're differentiating it with respect to. But because it's clear to me when I'm solving the problem, I'm okay with it. And then the rest is just isolated, so you eventually end up with y prime is equal to negative x over y. Not a big deal. Many people don't do that, but it's a clean, easy way to do it. You're not having to write as much. So let's move on then to a couple other ones, or more than a couple other, I guess. I think I've got on our handout, I've got like 5 or 4 at least. Now this one's same thing. We differentiate with respect to x. So we get 2x plus 2y, but then when we try to take the derivative of y, we just indicate it as y prime. So every time you try to differentiate the y variable with respect to x, it just gets indicated with y prime, meaning basically y prime represents the derivative of y, whatever it is, with respect to x. And then this means 3y. When you differentiate that, you need to be careful, because this one can be a problem. This is 3y1, so that would be 3 y to the 0, but then you still have to have your y prime. Anytime you try to differentiate that y, you have to indicate it with a y prime. Derivative of 10 would be 0. And the thing is with this problem is we do have 2 y prime terms, so we keep them on the left or take them to the right, doesn't matter which. I'll keep them here. 2y y prime plus 3y prime is equal to 2x, negative 2x. And then to get the y prime by itself, we factor it out. So y prime comes out, and we get 2y plus 3 is equal to negative 2x. And then y prime is equal to negative 2x over 2y plus 3. So through division, you get it in that form. So again, these are the key steps, making sure that when you have a y variable and when you differentiate with respect to x, it will be a y prime. Let's go on to the next one. Gradually raise the bar on each of these. Now this has got a whole new thing going on that can be troublesome. We differentiate this whole thing, and we get 2x. Now the problem is this middle term, because xy we must use the product rule. And I'm not going to write out the steps as I use the product rule. I'm going to do it really quickly because we know it's a simple expression, just x times y. We know that the product rule is the derivative of the first term, first function, multiplied by the second one, plus the first one in its original form, times the derivative of the second. So we take the derivative of x, which is 1, and we're left with just y. And then we keep the x by itself. It doesn't get differentiated. But when we try to take the derivative of y, we have to indicate that it's y prime. And we need to put a bracket around the whole thing because we're subtracting the original term. And that's where people make mistakes. So when you do the product rule on that xy term, put a bracket around there. It wouldn't have mattered if it was plus xy, but because it's being subtracted, it's going to affect the signs. And then the next one is 2 times 2 is 4y, but don't forget, then you got to differentiate the y, so you get y prime, and this is then equal to 0. So clean it up. 2x minus y minus xy prime plus 4y y prime is equal to 0. And keep the y prime terms on the left side, or you may want to. And I'll put the positive one first. 4y y prime minus xy prime is equal to, the negative y comes over, making it positive y, and then subtract 2x away, and we get minus 2x. Factor out a y prime, and you get 4y minus x, and that's equal to y minus 2x. Then when you divide by both sides by 4y minus x, you'll get this, y minus 2x over 4y minus x. And then you're done with it. So be careful with a question like that. It's easy to make mistakes with it, particularly on that xy term. Next one. Number 4 is a bit of a trick question because you could be using the quotient rule on this. So you could use the quotient rule, but it's easier to simplify it first. That's what I would advise you to do. By simplifying, I would multiply both sides by x minus y, or if you like to think, the forbidden act of cross multiplication. So 2 times x minus y is equal to x plus y. And then when you simplify, 2x minus 2y, distribute the 2 in, is equal to x plus y. And you could do this a number of ways. I'm going to keep the y's on the right side, so I'll bring the y's, add 2y on, giving me 3y. I'll subtract an x away, so I get x. So y is equal to 1/3 x. I divide by 3. So we end up not even doing anything with this. dy dx, we take the derivative of both sides, is just equal to 1/3. Now, had you used implicit differentiation on this and the quotient rule, you'd have got yourself into some trouble. You would have probably got it right, but it would have been a lot of work. So I would recommend that you always keep an eye open for simplification. Now here we go with traditional derivative questions. We want to get the slope of the tangent line to this function, or this, excuse me, not a function, this equation, specifically at square root 2, 1. Now that's not a big deal. Now notice you were given the y-coordinate, which is kind of nice. We differentiate with respect to x, just like we always do. So we would get 5y to the 4 y prime. Now we have to use the product rule on this one. So the product rule would state we take the derivative of the x squared term, so that's 2x multiplied by y, added to the x squared by itself times y prime. So then our attempt to differentiate the y, and then minus 4x is equal to 0. Now that bracket did nothing for us. So 5y4 y prime, I'll rewrite it without the bracket. So x squared y prime minus 4x is equal to 0. Get the y prime terms together. I'll keep them on the left. So 5y to the 4 y prime plus x squared y prime is equal to 4x minus 2xy. Factor out a y prime from each of the left side terms, and you'll get 5y to the 4 plus x squared. And then we're off and running. So y prime is equal to 4x minus 2xy over 5y to the 4 plus x squared. So that's our derivative, and everything's looking fine. But we need to now find the slope at this point. So in order to do that, we substitute in our x value, because the derivative, of course, represents the slope. So we get 4 root 2 of the tangent line minus 2 root 2 times 1 all over 5 times 5 times 1 to the 4 plus root 2 squared. So y prime is equal to, well, 4 root 2 minus 2 root 2 is 2 square root 2. And then the denominator would be 5 plus 2, so 7. So this would be the slope of the tangent line at root 2, 1 is 2 root 2 over 7. Let's try a couple more questions. Find the points in the circle where the tangent line is A, horizontal, and B, vertical. Really common questions. Now this is described as a circle. For those of you who took 30 Pure might recognize it being in general form. It is a circle. And interesting with a circle is that at some point we would expect the tangent line to be horizontal and vertical. So this can help you find the endpoints of circles or ellipses instead of using the conventional completing the square method. You can differentiate it. So this is what we have to do. And we note that if we want the tangent line to be horizontal, it means I'll just say m is equal to 0, but that would also be the derivative. So dy dx is equal to 0. And then if it's vertical, it would mean that m is undefined. So dy dx is undefined. So when we differentiate this expression, we'll get 2x with respect to x, 2x plus 2y, y prime, plus 8 minus 6y prime is equal to 0. So our y prime terms, 2y prime minus 6y prime, keep them over there. Doesn't really matter. You could have taken them wherever, but I've done it now, so I'll keep those where they're at. And then the negative 2x minus 8 goes to the other side. So y prime will leave us with, no, I'm missing something here. 2y prime, I think. 2y, yes. So sorry, this should be 2y prime. So 2y, you're wondering what's going on with that. So y prime comes and we have 2y, there we go, minus 6 is equal to negative 2x minus 8. So we're off and running now. And then we get y prime is equal to negative 2x minus 8 over 2y minus 6 through division. Now, you probably will prefer to factor out, say, a negative 2 on top, leaving you with x plus 4, and then a 2 on the bottom, and then that'll leave you with y minus 3. And then when you divide the 2's out, you'll get y prime is equal to negative x plus 4 over y minus 3. However you want to write that. Now that step wasn't absolutely necessary, but it gives us a nice easy form. Now for it to be horizontal, question is, this is occurring where dy dx is equal to 0. So therefore, where 0 is equal to negative x plus 4 over y minus 3. And then you've got to think. We've seen this before. If it's equal to 0, you could solve it mathematically, but it's easier to ask yourself, where is the numerator? Equal to 0. So negative x plus 4 equals 0 means x plus 4 is equal to 0 if you divide by negative 1, so x is equal to negative 4. Now that's your x-coordinate where it's horizontal. But now to find y, you need to take that value and sub it into the original. To find y, plug in your x as negative 4 into the original expression. So negative 4 squared plus y squared plus 8 times negative 4 minus 6y minus 11 is equal to 0. So 16 plus y squared minus 32 minus 6y minus 11 is equal to 0. And you'll get y squared minus 6y. Get all your numbers together. Minus 16 minus 11 is minus 27 is equal to 0. And then when you factor that, you'll get y minus 9 times y plus 3. So I'm going through this algebra part pretty quickly, but I trust that you can handle those ones fairly well. So it means there's going to be 2 points. And this actually makes sense to us because if it's a circle, there should be 2 at the top of the circle and the bottom of the circle where the x value, or where the tangent is horizontal. So I'm going to bring this one up in the next screen. So, oops. Okay, so at x, let's try again. X is equal to negative 4. Y is equal to 9 and negative 3. So therefore, the tangent line is horizontal at negative 4, 9 and negative 4, negative 3. And then for the vertical one, we can handle this too. The thing of it is, dy dx is undefined. And in here, you need to be thinking, okay, where would this expression be undefined? Seeing as you got negative x plus 4 over y minus 3. And its question would be, where is the denominator? Equal to 0. So y minus 3 equals 0, and you'll get y is equal to 3. So now you just find x coordinates. So this gets substituted into the original expression again. So you've got that down someplace. So sub it in, and x squared plus 3 squared plus 8x minus 6 times 3, 6y, minus 11 is equal to 0. So x squared plus 9 plus 8x minus 18 minus 11 is equal to 0. So x squared plus 8x minus 9 minus 11 is minus 20 is equal to 0. So we get x plus 10. X minus 2 is equal to 0. So x equal negative 10, x equal 2. So therefore, the tangent line is vertical at negative 10, 3, and 2. X is 2 and y is 3. You could graph this at this point now. You could find the midpoint, all sorts of cool things you could do with it. Do one more question. We've been running on for a long time here. This is not anything really remarkable, except that there's one thing, and that is where we differentiate this with respect to x. Very similar to a question we did earlier. We'll get the derivative of x is 1 times y, using the product rule on this inner part, plus xy prime plus 2y is equal to 0. So we've seen a version of this question earlier. So you're thinking, well, what's going on with this? Why is this worth spending any time on? Well, later on we're going to run into something here pretty quick, so I want to be aware of that. So I'm going to take the xy prime to the other side, and and pay attention to what I'm doing, 2y prime. Try not to go through this thing too quickly. So I'll take this to the other side, so minus 2y prime, so we're doing better. So pay attention, and then you'll be okay. Now, when you factor out a y prime, you'll get x minus 2y, and that's equal to 2x minus y. Now, this question, by the way, does just ask for the x coordinates. So y prime, the derivative, which we need initially, is 2x minus y over x minus 2y. Now, where is this horizontal? So where is the numerator? 2x minus y equals 0. What we end up getting, unfortunately, is where 2x is equal to y when you solve that. Now, it doesn't matter which variable you solve for, really. But what I'm going to have to do now, it's not giving me an answer immediately. It's just giving me one variable in terms of the other. So I have to go back into this and replace in. Everywhere I see a y, I replace it with 2x. So x squared minus x times 2x plus 2x squared is equal to 12. Now, had you isolated the x and replaced the y in, the problem is you'd have been getting the y coordinates. So in this case, it wouldn't have been the right play, although often you want both the x and the y. So I'll finish this one off. I get x squared minus 2x squared plus 4x squared is equal to 12. So that's going to give me 3x squared. When I get all the x squareds together, is equal to 12. X squared is equal to 4. So x is equal to plus or minus 2. So at x equal plus or minus 2. So if you wanted the y coordinates, you would just have to go back and get them into the original. So I'm going to stop there. That's a fairly long lesson. And we'll be playing around with these type of questions later on in sort of a more complex way. But this will get you going on it. So thank you for your time.